Welcome everyone to Physics 1. I'm going to introduce a few orders of business here about how the class will be run, and then we will be jumping into some content even in this first lecture. But before we get there, I want to go over some things. I would encourage you to take a look at the syllabus, which is posted on Blackboard, that goes into most of these things in greater detail. But for now, I just want to give you an overview of some important questions before we get started. So, being that we are teaching this class remotely and you will have to be doing all of your work essentially online, it probably goes without saying that you need to have reliable internet access in order to accomplish all of this. Um, Anytime Pitt holds these summer courses in a 6-week session, all the material of an entire semester is compressed into only 6 weeks, which means that it's very intensive. Combining that with the fact that you're doing this all online means that you need to have reliable and consistent access to the internet. If you are in a situation where you are sharing a device with someone, you might want to be aware that this will be a time intensive course and you will need to be able to have access basically every day on your device. Now, twice during the 6 week session, there will be oral exams in which you will need to have audio and visual conferencing capabilities. So I'm trying to make this not too burdensome. It's only going to be 2 times that you need to do this in order to participate in the oral exams. There will be other conferencing that you should be taking part in, but for those particular meetings, you will not necessarily need to have the ability to share your own audio or video. You can keep those things shut off as long as you can hear what's going on, and possibly type or into a chat window if you have questions, or if you're using some sort of a tablet, being able to write on your screen if that's your preference. But for those 2 oral exams, you will need to be able to share your audio and your video so that we can see and hear one another. In addition, there's the standard materials that one would need anytime you are taking Physics 1, and that would be some sort of a scientific calculator or a graphing calculator. As long as it's capable of doing trigonometric functions, you're good. You do still need a textbook, even though it is an online class, because your homework assignments are going to involve you doing some of the back of the chapter questions out of the textbook. So if you have not yet ordered this textbook, I would encourage you to get it as soon as possible. It is the Halliday and Resnick 11th edition. So go ahead and try to find that used if you would like to save some money. It doesn't really matter if it's new or used as long as it's the 11th edition. And then if you want an extra resource to look at, there's a free recommended textbook. All you got to do is go to this link here, and you'll be able to access that textbook online anytime you like. And it contains a lot of the same material, but it will give you an opportunity to see it from a different, from someone else's explanation, and or do some additional practice problems. The nice thing about this particular textbook is that it has a student resources section which includes full solutions to some of the chapter questions. So that allows you not just to see if you've gotten the right answer like you would normally do when you look in the back of a textbook to check your answer, but it will also show you the correct solutions so that you can see how you got there. Okay, so those of you who have been with Pitt before may be aware that we're in the midst of making a transition from Blackboard as our course web to Canvas as our course web. If you're not familiar with that, it's okay too. But many of the classes, if you're taking any other classes this summer, they may be taking place on Canvas. I wanted to let you know, though, that I have chosen to stick with Blackboard for the summer class. I was an early adopter to Canvas over the spring and got the opportunity to see how it functions. Although I wanted to like Canvas, I came away from that experience strongly disliking Canvas, particularly as it applied to what I discovered to be the case for online instruction, because we had to switch to the online instruction partway through the spring semester, and some of the capabilities were not what I would have hoped, and the classes that I was teaching still on Blackboard didn't run into some of those snags. So I am sticking with Blackboard. In order for you to access your Blackboard course, you basically just need to go to your PIT portal and find where it says Blackboard, and then choose the course number that corresponds to this course, Physics 1, which is Physics 174. It may be your only course there if this is the only course you're taking, or if this is the only course that's taking place on Blackboard instead of Canvas. But that's the typical way you'll go about accessing your class. So, as far as how the online learning will take place, what I'm envisioning is that I, again, am trying to make this not burdensome for you and require a lot of synchronous activities. As such, I will be asking you to watch video lectures just like this one on the YouTube playlist that corresponds to this class. Be aware that I have many lectures on my YouTube channel corresponding to several different courses, so you do not need to look at, and you're not encouraged to necessarily look at the other lectures because they may not necessarily be relevant to what we're talking about. You really just want to stick with the playlist that corresponds to this course so that you're sure to get all of the material that you need. Now, you are allowed to watch those video lectures when it's convenient for you to watch them, with the exception that there are 2 Thursday lectures that I have scheduled throughout the 6-week session. There are only 2 of them, where you must attend those 2 lectures synchronously. They occur on July 2nd and July 16th. The rationale behind these is that we can all get on the same page in the Thursday, the last class leading up to the week in which oral exams will take place. So July 2nd, we will all meet synchronously for a live lecture that date, and then the following week you will have your first oral exam, and then later on July 16th, actually I need to double check that date. It might be a little different in your syllabus. If it is, go with what the syllabus says, but there is another date in there in which there's a live lecture that should be attended synchronously, and then the following week after that you'll have your second oral exam. So that's an opportunity for you to ask questions going into the oral exam and make sure you're prepared. As for the recitations, your TA will be holding these virtually. I still have to meet with your TA to nail down whether this will be like a typical office hour, or if it will be, it may incorporate some amount of her demonstrating some example problems. And either way, though, the work that you will be doing, you'll do sort of on your own and then submit it to CourseWeb so that your TA can grade it. This work will include creating your own problems along with solutions to those problems and designing experiments. Read up on that more in the syllabus if you want to know the details about those particular types of assignments. In addition, you'll be asked to participate in a discussion board feature on Blackboard that the TA will monitor and be able to give you feedback. And there you can ask questions, share ideas, and so on, and just develop a sense of rapport with your TA and with one another. In terms of your homework assignments, these are going to be integrated into Blackboard. They will include some multiple choice questions that will be graded instantaneously once you submit the assignment. And then there will be some open-ended questions that you may have to wait to have graded, as well as every assignment will include a part where you're going to need to upload some images of the textbook problems that I mentioned earlier that you worked out from the back of each chapter. Now, make sure you know how to combine. If your homework took up more than one page and you had to take multiple images, make sure you know how to combine those into one single file. There are many ways to do this. You can drop them into a Word document, for example. If you are running Apple, you can bring them up in preview and then drag the thumbnails from one into another and save that as a single file. Or you can use an app called Cam Scanner, which will allow you to take multiple pictures and save it as one PDF. Do what you like, but Blackboard only allows one file to be uploaded, not multiple files. So those images just need to be combined. So, make sure you figure all that technical stuff out. And then when you're waiting for the assignment to be graded, just be aware that mostly the assignment is going to be graded on completion. Of course, the multiple choice questions will be graded on accuracy. And in addition, those textbook questions that you've answered, 1 to 2 of these questions per assignment will be graded based on accuracy, but I will not necessarily announce in advance what questions those are. So be prepared for all of them and make sure that you show your work so that you can get partial credit. If you would like additional problems for practice, then I will also be making a Lon Kappa homework system available for you. This will not count for credit, but it will allow you to get extra practice, especially as you're preparing for exams. Speaking of exams, as I mentioned earlier, these are oral exams. They will take place during weeks 3 and week 6. And they will cover the material from the previous 2 weeks. So that is to say that on week 6, when you take that oral exam, it will not be comprehensive. It will only cover weeks 4 and 5. How we will run these is essentially that we will coordinate, you and I will coordinate to find a mutually agreeable time from a certain number of time slots that I'll make available. And this will be an individual endeavor. You'll be given 30 minutes during which to take this oral exam. So it will not be a very long exam. You can even think of it sort of a larger quiz. And I will leave it up to you to decide if you prefer to work on Blackboard Collaborate or Zoom. Sometimes your device may work better or worse with one or the other of these. I'm perfectly happy to do either. So when we coordinate, you can just state what your preference is at that time. Okay, and I really hate to be having to say this, but I wanted to take a moment and talk about academic integrity. In the spring semester, just be aware that there were students in the introductory physics classes who were taking online tests, and they were caught cheating on these tests and received failing grades for the class. It's possible for us to track these things. We were able to prove cases of cheating, and just because it's online doesn't mean that you have access to any tool that you want. You still have to abide by the rules of academic honesty that the university expects. And I won't hesitate to pursue future cases of academic dishonesty if there's any sort of violation to this academic integrity. So just assume that any online work that you submit will be scrutinized carefully to be sure that you're abiding by the academic integrity that the university expects. If you want to see the policy on that, please take a look at your syllabus for the details of what constitutes academic integrity violations. Okay, so with all of those nuts and bolts out of the way, I want to introduce myself and take a moment to invite you to introduce yourself, which we'll do by way of the discussion board feature on Blackboard. So who I am a member of the physics faculty. My research interests are basically physics education research. In the past, I have been involved in observational astronomy research as well, but at this point that's mostly armchair. I am from Pittsburgh originally. I'm a mother of 4. I have various hobbies that I enjoy taking part in, many of which you can see listed here. And I just wanted to show you this funny comic that I saw on Facebook that kind of talks about how geeks like me are the kind of professor you have to look forward to. So as far as you, we have a small number of students this semester, or this session, I should say, which is nice in the sense that we can get to know one another. And so I would like you to take a look at the prompt that you'll see in the discussion board once you log on to Blackboard, and take a moment to introduce yourself, and we'll get a chance to get to know one another through that. Okay, so it's time now to jump into some of the material. We're going to start with Chapter 2 in Halliday and Resnick. So that may be seeming to jump the gun a little, but I regard Chapter 1 as basically something that you should already have some knowledge of, and some ability to understand on your own at this point, given the prerequisites and expectations for this class. So if you feel a little weak in that area, just take a look at Chapter 1 and make sure you get up to speed. We're going to start, like I said, with Chapter 2. We have a lot of ground to cover in a short amount of time, so there's really no time to go back and make sure that we do Chapter 1. I'll expect that you have done that on your own. So the first thing I want to mention is the SI units that we're going to use in this course. Basically, every unit that we construct is going to be some combination of these three fundamental units, which are the kilogram, the meter, and the second. For those of us who grew up in this country, we don't necessarily have an intuitive grasp of at least two of those. We might have some idea about what constitutes a second, but just to give you an example, a kilogram as a unit of mass is approximately the same as the mass in a small cantaloupe. A meter is the length of this acoustic guitar here. And a second is about how much time goes by when you take 2 steps at a comfortable walking pace. Another tool that we're going to need to start discussing Unit 1 is the idea of a vector. A vector is a quantity which includes both magnitude and direction. You may see it indicated graphically as essentially just an arrow, like this arrow that's labeled A. And the length of the arrow tells you something about its magnitude, the amount, and the direction of the arrow then obviously tells you the direction of the vector. We're also going to need to work with symbolic representations of vectors. Sometimes you'll see that as basically an arrowhead on top of some other symbol, or you may see it as a bolded symbol. And while I'm mentioning these things, it's also probably a good time to mention that we make copious use of subscripts in our vectors. For example, you might see X with a subscript I to mean X initial, or you might see it as a subscript O, or you might see X sub F or X final. But really, we can make these subscripts be anything we choose, whatever seems to be convenient for the problem that we're considering. Okay, so get used to this idea of a subscript, and in fact, you can use whatever subscripts you like, and what makes sense to you. If you have a particular method or conventions that you're used to, you can stick with those. Okay, so when we draw, let's go back to this graphic representation of a vector. When we draw a vector on a coordinate system like you see here with vector A, we can think of this vector's direction as consisting of some direction in the horizontal aspect and a little bit in the vertical aspect. So it's sort of horizontal and sort of vertical. It's some combination of the two. And these separate aspects are what we call components. So whenever you are looking at a vector, you can think about, the jargon is, resolving it into components. And the components then add vectorially to give you the vector that you see. Now, a word of caution, if this vector, if this x component is, say, 3 units long, and this y component is, say, 4 units long, that doesn't mean that this a component, just because these add vectorially to give me the vector a, does not mean that the vector a is 3 plus 4. We have to be careful to make sure that we add things in a way that is a vector and not a scalar. So let's take a look and explore that more in detail. Vector addition requires that we consider both magnitude and direction. The only way that you can get vector addition, where you have a vector 3 plus a vector 4 giving you a vector of length 7, is if you have them pointing in the same direction, like what you see here. Then this 3 units plus this 4 units would give you an overall vector that is 7 units in length. But if you have some other direction to one of these, then that's not going to work for you, and you have to be careful to add the components together. The components can be added together that way because they are, by definition, pointing in the same direction. So in this particular example here, where you see that c, the vector c, is equal to the vector a plus the vector b, then if I look at the components of a, then the x component to my c vector will be the ax component, or the x component to a plus the x component to b. They're pointing in the same direction, and you can see that this blue dotted vector plus this little blue dotted vector gives you this dotted c vector, which is the x component of the vector c. Okay, and we could do the same thing with the y component. cy is going to be equal to ay plus by. Okay, but then if I want to know what the length of this vector c is, now I'm sort of back to the same thing that I had on the other slide, where I've got an x component and a y component to this vector c. Now I know that the vector cx plus the vector cy gives me the vector c, but how do I figure out what the magnitude is of c? Well, for that I need to use the Pythagorean theorem. This dotted vector cy could be moved over here, and you see that it forms a right triangle for which the vector c is the hypotenuse. And so for this right triangle, we apply the Pythagorean theorem, and then we can say that the magnitude of the vector c is going to be equal to the square root of the magnitude of cx squared plus cy squared. Okay, so anytime you're engaging in vector addition, you have to just be careful to consider both the magnitude and direction of the vectors that you're adding. Okay, we can also multiply vectors. Now, there are 2 ways to do this. The second of these 2 ways we will not get to for a couple weeks. So I don't want you to forget about it entirely, but it's not the first of the 2 types of multiplication that we're going to meet. Firstly, we're going to run into what we call the dot product or the scalar product. Purists might like to call it a scalar product because what is returned from this multiplication is a scalar quantity. That scalar quantity is equal to the product of the magnitude of those 2 vectors times the cosine of the angle between them. For the vector product, which again we'll meet in a couple weeks when we start talking about torque, and I don't wish to at all downplay its importance. It's going to be very important to you when you get to Physics 2, in fact. But this is what we would call the cross product or the vector product. Vector product implies that it returns a vector, and in fact it does. The magnitude of that vector is very similar to what we would do for the scalar product. It's just that we're going to multiply by the sine of the angle between them rather than the cosine. In order to determine the direction of this, that's just the magnitude of the vector product. In order to determine its direction, we generally do something in physics called the right-hand rule. And I hate calling it the right-hand rule because there are actually many ways that you could implement this right-hand rule. But we'll talk more about how to do that whenever we start talking about torque. But you can take a look at these cartoons and they give you some sense of a couple different ways that you could do a right-hand rule to determine the direction of your vector product. Basically, you just want these things to be mutually perpendicular to one another so that this vector A times this vector B will give you a vector in this direction. Okay? You'll get plenty of practice at that in a couple weeks. Okay, so with those tools, let's start talking a little bit about motion. So let's consider that we might have a particle that starts out at point P. You see here on this coordinate system. Then it executes some motion, and at a later time it ends up at point P2. So we could describe the displacement of that particle, and that displacement would involve a vector quantity that has both magnitude and direction. A vector quantity which starts at P1 and ends at P2. That's its direction, as you see, and the distance between these two would then be the magnitude of that displacement vector. For this displacement vector, though, the path does not matter. All that matters is your initial and final position. So it's as if we looked away and then looked again and saw it at point P2. It could have executed some meandering path like this, but in terms of the displacement, it's only gone from P1 to P2. That's the displacement vector that we are going to use. Now let's contrast that with distance. So distance is a scalar quantity which involves the total length of the entire path that you took. So now the path does matter. It's the magnitude of your entire path that you've taken. So let's say that you and a friend both start out at the same position and you both end up at the same position later on, but to get to your destination, maybe you take the long way, you take the scenic route, and your friend takes the most direct route. If you're driving there, then your odometer is going to show that you've traveled more miles than your friend has, and so that's because you've gone a greater distance. So distance and displacement are not entirely synonymous with one another. You have to think about the entire path length for distance, whereas for displacement it's just what is the difference between your initial and your final position. Okay, another quantity we need to discuss is velocity. Velocity is a vector quantity, meaning that it has direction and magnitude to it. Speed, on the other hand, is the magnitude of your velocity. It only has the magnitude, it does not have the direction. So if I say that I'm traveling 55 miles per hour, I've given you a speed. If I combine that information with, say, my GPS, and I say that I'm traveling 55 miles per hour east, now I've given you my velocity because I've given you both my speed and my direction. Both of these, for SI purposes, are in the units of meters per second, and in terms of symbolically, you can indicate velocity. Typically, this is conventionally done with a V and an arrowhead above it, and it is the time rate of change of your displacement vector. The speed, on the other hand, is just the scalar, the magnitude of that velocity. Another way to think about your motion is to think about a plot of your position as a function of time. So if you look at how the position of some object changes as a function of time and you plot it on a two-dimensional graph like you see here, position versus time graph, then the slope of this graph is going to be your velocity because again it's your time rate of change. So on average, that means that we could think about your average velocity as x minus x naught, for example, over t minus t naught. Which means we have a way now to solve for x and describe your position as a function of time. And that basically looks like this equation here that I'm writing. Now, of course, this is neglecting any acceleration that you may experience, and we'll talk about acceleration on the next slide. But for now, let's just say that the slope is going to be, the slope of your position versus time graph is going to be your velocity, and if that is if this path is curved on your position versus time graph, then we're going to use a tangent line in order to find the slope of that average velocity there. As far as your velocity changing, that's what constitutes acceleration. And notice that it's any change of velocity, which means that you could change the magnitude of the velocity or the direction of the velocity. That means that the speed could change or the direction could change. So you could speed up, you could slow down, or you could change directions, or any combination of those things, and you would have some kind of acceleration. Acceleration then symbolically is going to be indicated like this, an A with an arrow over the top, and it is the time rate of change of your velocity vector. In addition to considering a position versus time graph, we could also look at a velocity versus time graph. The slope of the velocity versus time graph is now the acceleration, just as the slope of the position versus time graph was the velocity. So when I'm looking at a position versus time graph in which there is a constant acceleration, now this shape looks to be quadratic rather than a straight line. It is your job to think about for the next time we meet why that's the case. I hope you've enjoyed this, and I will see you for Lecture 2.